So he received a PhD from Stanford in 2014, and since then he joined faculty of Department of Electrical Engineering and Computer Science of UC Berkeley in fall 2016. Since then he's a faculty there. And his work focuses on machine learning for decision making and control, with an emphasis on deep learning and reinforcement learning algorithms. And his research includes developing algorithms for end-to-end training of deep neural network policies that combine perception and control, scalable algorithms for inverse reinforcement learning, deep reinforcement learning algorithms, and more. I think having the workshop title is Deep Reinforcement Learning. I think this is the first talk, I think, that talks about the deep learning. Sergey, you can get started. Yeah.
Great. Thank you for the.
Okay, here's the right microphone. Okay, thank you for the introduction, and thanks to all of you for sticking around so late in the day. I know it's fairly late in the evening, but hopefully I'll make this a little bit more high level, maybe a little more exciting with a few more videos. So I'm going to talk about offline reinforcement learning today. And to start off the discussion with a little bit of motivation, let's ask a big question. Why does modern machine learning work? I think it's fair to say that separately from many of the algorithmic insights, two big ingredients in the success of modern machine learning have to do with using large data sets and using large and high capacity models. And what is it that modern machine learning does with these large data sets and large models? Well, it does primarily, if you work on machine learning in industry as a practitioner, it does things like recognizing objects and images, translating text, recognizing speech, tasks that have to do with some sort of recognition or perception. And these work very, very well if we have large data sets and large high capacity models. So it's tempting to define, outside of the audience of this workshop, outside of those of us that work on RL, it's very tempting to actually define machine learning as the discipline of doing prediction and doing recognition. But if we step back a little bit, we could ask an even more basic question: why do we need machine learning? And to get at that, we can ask a yet more basic question: why do we need brains anyway? And we can ask a fellow who knows quite a bit about brains. Daniel Walpert is a well-known neuroscientist studying motor control, has this to say on the topic: we have a brain for one reason and one reason only, and that's to produce adaptable and complex movements. Movement is the only way we have of affecting the world around us, and I believe that to understand movement is to understand the whole brain. This might seem a little reductionist, but I think there's a point to be made here that ultimately the way that you affect the world is the only thing that your brain needs to determine how to do, because that's your only output channel. So as a postulate, I might say that we need machine learning for one reason and one reason only, and that's to produce adaptable and complex decisions. Because whatever prediction or recognition problem your machine learning system is solving, ultimately it makes some kind of decision, and that's what actually affects the world. And this is obvious in some settings. If you're thinking about a robotics problem, the decision is how the robot moves its joints. If you're thinking about an autonomous vehicle, the decision is how do you steer a car. But you could say that, well, maybe my problem really does have to do with recognizing objects and images. What is the decision that is being made then? Is it the image label? I would say usually not. Usually it's what happens afterwards. So are you tagging a user in a photograph for Facebook, for example? Are you detecting the species of animal in a camera trap for some kind of ecological application? These are all decisions, and they lead to various consequences. So if you have a system that is capable of reasoning about decisions and their long-term consequences, a reinforcement learning system, then you ought to be able to manage these kinds of domains more effectively. Typically, we don't really think about non-RL problems in this way. We don't think about recognition problems or translation problems through the lens of decision making, because typical supervised learning problems have additional assumptions that make them easy, that make them much more convenient to view as supervised learning problems and very inconvenient to view as reinforcement learning problems. Things like independent data points, the fact that outputs don't influence future inputs, and the fact that ground truth labels are provided at training time. But a lot of the, a lot of the domains that we consider decision-making domains, autonomous driving, robotics, etc., don't satisfy these assumptions. Their current actions do influence future observations. The goal is to maximize some utility, such as the reward function, and the optimal actions are not provided. They have to be inferred, often from experience. But these kinds of challenges, they're not actually just issues in control. In many cases, these supervised learning assumptions that make things easy are really a simplification. Real-world deployment of these systems often has the very same feedback issues. To give you an example to illustrate this, let's say that you design an app for predicting traffic conditions, and then users will use this app to decide where to drive to avoid traffic. Now they will change their patterns based on the predictions from your app, which in turn will affect the traffic conditions. So your app, even though it seems like it's solving a prediction problem, really has to deal with the same kind of control, long-term consequences, and decision-making issues as the decision-making systems. So very often, these very convenient supervised learning assumptions actually turn out to be kind of false when you actually go to deploy your system in any practical setting. So if ultimately ML is always about making a decision, why don't we treat every machine learning problem like a reinforcement learning problem? Well, it's because reinforcement learning is really two different things. On the one hand, reinforcement learning gives us a framework for learning-based decision-making. So supervised learning, you think about a function that maps some input X to a label Y. Reinforcement learning, you think about a policy pi that learns to map some state S to an action A, which is a decision, and that affects the next state. So reinforcement learning provides you with a mathematical framework to think about these kinds of problems. But it's also something else. It's also an active online learning framework for control. So this is the classic diagram from the Sutton and Bartow textbook. But we can briefly summarize this diagram as essentially saying reinforcement learning is about an agent that interacts with the world, gets a little bit of experience, uses that experience to improve its policy or model, gets more experience, and repeats this many, many times. Now, as I argued before, having a framework for learning-based decision-making is very good because almost all real-world learning problems look like this. Almost all real-world learning problems are overtly or covertly decision-making problems. But when it comes to the active online part, almost all real-world learning problems make it very difficult to do this. There are some problems where active online interaction is very natural and very straightforward, but in most cases, it is logistically very difficult. It is very costly or expensive or dangerous. I'll get back to this point shortly. Now, this is a deep reinforcement learning or reinforcement learning focused kind of discussion. So, of course, an obvious objection is, well, it kind of works, doesn't it? Like, why do we have to worry about it? And it works in many different settings. But what I would say here is that the kind of domains where reinforcement learning has been successful, the kind that I have pictured on the left, some of which are very difficult, like beating the world champion at Go, are very different in a very systematic way from the kinds of domains where supervised machine learning techniques have been successful. And we can kind of guess what that factor is just from looking at the pictures on the left versus the pictures on the right. There's a big gulf, and it's not really a gulf of task complexity, it's a gulf of task diversity. The supervised machine learning methods in vision, NLP, and so on have been applied to open world problems. Classifying any image on the internet, things like that. These problems are characterized by very broad diversity, and they demand very broad generalization. In contrast, the bot that is playing Go doesn't have to worry about somebody spilling coffee on the Go board, right? It lives in a closed world environment with known and well understood rules. Within that environment, it might be solving a very difficult task, but it never has to venture outside of that closed world. So I think that's actually the challenge, that when you live in a closed world environment with known, well-characterized rules, and at least with known boundaries, then this active online framework is very straightforward. But once you venture outside of it, what you need is very large data sets in order to get generalization. Remember what I said in the beginning, we need large data sets and large models. And that's actually very hard to do in an active online framework. When you have to collect an ImageNet sized data set every iteration of your reinforcement learning algorithm, because you need that for generalization, then online active collection that has to be repeated for recollecting a data set the size of ImageNet. And that rapidly becomes completely impractical. So how do we make reinforcement learning look more like supervised learning? We don't want to do so by introducing really strong assumptions about things being IID or about having ground truth supervision, but we would like to free ourselves from the need for active online interaction. So remember that reinforcement learning is these two things. It's a framework for active online interaction, and it is also a framework for computational decision-making. Closely embodies the active online part. It's when you have a policy that interacts with the world, collects a little bit of data, uses it to update a policy, and interacts with the world some more. This is basically just the same picture, but with more symbols. In contrast, offline reinforcement learning allows us to get at the decision-making framework without worrying about the active online framework. And you can think of offline reinforcement learning as basically off-policy reinforcement learning, but taken to the limit. So we have some data set that was collected that I'm going to denote as D, and it was collected with some kind of behavior policy labeled here as pi beta. In general, we don't actually even need to assume that we know what pi beta was, just that it exists. So the data could have come from many different sources, humans, previous baseline policies, previous RL runs, whatever you have available to you. You're going to take this data set and you will use it to learn the best policy that you can pull out of it, labeled here as pi, without any active collection, and then you'll deploy it in the world. And this is very appealing because in the same way that you can take the ImageNet data set and train up the best image classifier, in the same manner, perhaps you could take a large data set of interaction with your system of choice and extract out the best policy. And if you're not happy with it, you can extract out another one without any additional data collection. So the overall workflow for a system like this would look like this, like the following. Collect a data set using any policy or mixture of policies, which could be humans performing the task. It could be an existing system performing the task. It could even be random behaviors or any combination of the above. And this is only done once. Then run offline RL on this data set to learn the best policy you can, essentially squeeze the best behavior you can out of the data set available to you, and then deploy this policy in the world. And if you're not happy with how well it does, go back to step 2, but you don't have to recollect more data to do this. And this kind of recipe could in principle be applied to domains that we don't ordinarily think of as reinforcement learning problems because online exploration or active learning is so difficult in those settings. Imagine, for instance, learning a policy for inventory management for a large multinational corporation. The corporation will go bankrupt if it were to deploy a partially trained policy for online exploration because too much money is at stake, but it has plenty of data available of how its warehouses were managed in the past that it could use to synthesize out the best possible policy. Imagine a policy that suggests plans for medical diagnosis and treatment to doctors. You don't want to experiment on your patients with random exploration or epsilon greedy exploration, but it's quite reasonable to get lots of data of previous prescriptions and treatments and then recommend the optimal course of action as determined by the offline RL method. Schedule in the course of scientific experiments, controlling power plants, controlling robots. All of these tasks could in principle be attacked with offline reinforcement learning, even though they are extremely difficult, oftentimes with online methods. So in the technical portion of today's talk, I'm going to tell you a little bit about some of the technical reasons why offline RL is challenging, why standard RL algorithms that we've developed for other settings are difficult to apply naively, how we can design offline RL methods, how we can evaluate them, and lastly, how we can apply them. But let's start with the challenges. So first, a quick primer. I mean, I realize this is the last talk in a long series of talks, so presumably all of you are very familiar with this. So this is mostly just to set the notation. You have an agent that interacts with the world that chooses an action A. The world responds with a state S and a reward, and your goal is to choose a policy, pi of A given S. The objective is to maximize the sum of future rewards or the sum of discounted future rewards. And a very useful object for this, of course, is the Q function, which is the total reward you will accumulate if you are in state S, take action A, and then follow your policy pi. And we know that if we can get the Q function, we can extract a better policy by using the greedy policy, by using the argmax. And we can also just shortcut this and directly try to learn Q star by minimizing the difference between the left-hand side and right-hand side of the Bellman equation. And of course, the nice thing about this is that this forms the basis of algorithms like QLearning and fitted Q iteration, it does not require SA and S prime to have come from any particular policy. In principle, enforcing the Bellman optimality equation could accommodate transitions from any policy. And of course, we're going to use this as the basis for our offline RL methods. So typically what we would do with this is we would just minimize something like the squared difference between the left-hand side and right-hand side. This is essentially what fitted Q iteration does. And we can write that as a kind of regression problem onto target values yi. And for this talk, I'm going to focus entirely on approximate dynamic programming methods, basically methods based on QLearning or Q function actor critic. I will say that there are other methods for offline RL not based on these principles, methods based on importance sampling, for instance. I just won't be covering them in today's talk, but they do exist. So one question we could start with is like, okay, fitted Q iteration gives us a way to use off-policy data. Can we use that to basically get an offline RL method? Very simple idea. You don't need off-policy data to compute the right-hand side. SA and S prime can come from any policy. So a very straightforward procedure that has been known for over a decade at this point. Collect some data set using some policy, add it to your buffer, and then in an inner loop, sample a batch from your buffer. Take some gradient steps on the difference between the left-hand side and right-hand side of the Bellman equation, and repeat this some number of times. And you could go out and collect more data, or you could skip this step if you're doing fully offline RL. We can think of it graphically as you're interacting with the world, you're pulling in some transitions, you have this big bucket of transitions available to you for training, you're crunching away on all the transitions in that bucket with your off-policy QLearning method, essentially your fitted Q iteration method, and occasionally you come back and collect more data from the environment. And basically all widely used QLearning methods fall into this basic recipe, including DQEd and all of its variants. So if we want to turn this into an offline method, we could imagine just skipping this step. And that's not an unreasonable idea. Of course, in practice, we would do some offline training and then maybe we do some additional online fine-tuning. That's kind of the more typical way to do this. But the question I'm going to ask here is, well, does this work, right? So in principle, we could simply stop exploring. We could start with a preloaded buffer and just train our Q function on that. But does that work? Does that actually give us a good Q function? So about 3 years back, we conducted a large-scale experiment at Google to study generalization in robotics by means of essentially a continuous action generalization of QLearning. So the setup was that we had a large data set of previously stored experience. Our data set was actually larger than ImageNet. We had multiple robots that were collecting experience all in parallel, and we were collecting both off-policy data and on-policy data, and then using a large-scale parallelized QLearning system to train a Q function on this data. And we wanted to see if we could get a robotic grasping system, in this case, a system that could grasp any object that would generalize effectively using this type of large-scale reinforcement learning. So did it work? Well, the short version is in some form, yes. So what you're seeing here are some videos of the trained policy. You can see it responds in some interesting way, even to some adversarial human behavior where someone like pushes an object out of the way and it reacts in real time. It can pick up objects in dense clutter, small objects, large objects, transparent objects. On a test set of never before seen objects, it gets a success rate of 96%. So we were pretty happy with it from an application standpoint. But for the purpose of today's talk, what I want to show you is some results about how this method did in offline mode versus with online fine-tuning. So we did actually test this. We tested fully offline QT-opt and fine-tuned QT-opt. The fully offline data set had 580,000 transitions. 580,000 episodes. Each of them was about 10 transitions. And the fine-tuned data set added an additional 28,000 online collected transitions with the latest policy. So the increase to the data set is negligible. Probably the difference between offline and fine-tuned is not the data set size, but something about the provenance of that online data. The success rate was 87% for the fully offline method and 96% for the fine-tuned method, which might not seem like a big difference, but if we flip it around, if we look at the failure rate, we can see that the offline method is getting a failure rate more than 3 times larger. Now, clearly that can't be explained by just the data set size. And even though both systems work, we're clearly paying a really heavy price for staying fully offline. And this is in a kind of a best case scenario with very diverse data collected by past RL policies. So something is going on here. There's a question in the chat. In real world systems with high dimensional state and action, how do we determine whether our data set is extensive enough? Yeah, that's a really good question. And I think that question actually connects very well to what I'm describing here. We made sure very carefully in this case that our data set was extensive enough by actually collecting it with highly randomized policies that we get good coverage. But in general, this is a really big challenge. You know, there are some theoretical results that show that in order to have reasonable guarantees of approaching the optimal policy, you need, you know, some kind of coverage assumptions that the data set basically covers the sorts of states that would be visited by an optimal policy. I think these assumptions are, you know, they can be derived in theory. It's a little bit harder to connect them with practice, you know, to show what it really means to have states from the optimal policy. I'll talk a little bit more about coverage in a more informal way towards the end of the talk. Okay, so what might be happening here with this heavy price that we pay for staying offline? The fundamental problem is that offline RL methods need to respond to a kind of counterfactual query. Let's imagine an autonomous driving scenario. Let's say you have data from human drivers, and they're not perfect drivers. You know, they sometimes make mistakes. They sometimes violate the rules of the road a little. Maybe they will run a red light, or they will occasionally, you know, swerve a little bit unsafely or exceed the speed limit. But on the whole, they mostly stay safe. The policy, when it is learning using that data set, needs to figure out, for example, what would have happened if it were to take a different action in a state that was seen in the data set. Would that be good or would that be bad? And how can it possibly know if it didn't see this in the data? The issue is that some of these counterfactual questions cannot be answered using the data set that was provided, and therefore the algorithm should not attempt to answer them. Online RL doesn't have to deal with this because it can actually try this weird unseen actions and see what happens. But offline RL has to somehow account for these actions being unseen or out of distribution, ideally in a safe way, while still making use of generalization to come up with behaviors that are better than the best things seen in the data. So you do have to generalize to new actions, but at the same time be aware of the fact that for some actions, you just can't produce an estimate. And that's very challenging. More recently, a few of my students, principally Abhiral Kumar and Justin Fu, studied this question in a more controlled setting. So we collected some data from the half cheetah benchmark in the GYM benchmark suite. And we wanted to see what would happen if we take good data, in this case, replay buffer data, basically, and retrain on that data with offline RL. And we saw that performance would drop when learning started. So we figured, well, maybe this has something to do with overfitting. So let's try varying the data set size. So blue here shows a data set size of 1,000, red shows 1 million. Training is fully offline. The y-axis is the reward, and the x-axis is the number of gradient steps. So you can see that increasing the data set size doesn't really make much of a difference. We can, however, inspect the learned Q function to see how that does. Now remember, the Q function is an estimate of the expected future reward. So the Q function is essentially predicting the quantity on the left. The y-axis here is a log scale. So what this is showing is that the red curve, the curve with 1 million data points, is getting negative 250 reward. It thinks it'll get 10 to the 7th power. Whoa, that is a lot of optimism, right? That is a very optimistic Q function. It thinks it's going to get 10 to the 7th power, but it ends up getting negative 250. So that maybe gives us a clue about what could be happening. Whatever is happening that's breaking these methods in the offline setting seems to have something to do with overestimating rewards.
Yeah, there is a question that says that what is the difference between offline RL and imitation learning?
Yeah. So I'll actually talk about this more towards the end of the talk, but the short version is that they are very different. Imitation learning assumes that your data came from an expert policy, and your goal is to do whatever was done in the data. That is not at all the case in offline reinforcement learning. The case in offline the goal in online reinforcement learning is to get the best policy you can based on the data that you were provided. And this data can be significantly better than the average behavior in the data set. So basically, there's kind of the wrong mental model, which is you're trying to imitate the data. And then there's the right mental model, which is you're trying to look at the data and use it to understand the system, and then squeeze out the best behavior you can based on that understanding. So you get very different results if you do this. And I'll show some examples of this later in the talk. Okay, so in order to understand this problem, this massive overestimation problem, we need to understand distributional shift. So this is, again, this is something that for many of you will be very familiar. If you have a supervised learning problem, in this case, a supervised regression problem, and you minimize the loss on some training distribution, what you're really trying to do is you're trying to minimize the expected value of the loss under the distribution over inputs induced by some P of X, right? So typically you have samples from P of X, you minimize the empirical risk, and you hope that minimizing the empirical risk is a good proxy for the true risk, which is this expected value. And at this point, you could ask some questions like, if you have some other test point X star, is your prediction F theta of X star correct? Well, so perhaps surprisingly, the answer is not at all clear cut. You know that your expected value of your loss is low under the training distribution P of X. In general, it is not low for some other P bar of X if P bar is not equal to P of X. And in general, it's not even low for some other point drawn from P of X, right? The error is only minimized in expectation. It might not be low point-wise. Now, the deep learning practitioners among you might be thinking, well, usually we don't. Well, so this kind of distributional shift business is really a worry for theoreticians, those of us armed with giant neural networks. And actually, I would ordinarily be very sympathetic to that viewpoint. But what if you pick your test point specifically by looking at your learned function F theta of X and maximizing it, right? So let's say the green curve is your true function and the blue curve is your learned function. The blue curve is very close to the green curve in most places, but if you pick the max, and of course I drew this picture intentionally in this way, if you pick the max, you actually get the point that exaggerates the error maximally. And this is, of course, how adversarial examples are constructed, right? Adversarial examples are constructed by optimizing an input into a neural net to produce a desired output. So maximizing the output of a real valued neural network is just a particular way to construct an adversarial example. And we know that it's very difficult to defend against this. So if you try hard enough, you will probably find an input that fools the model into producing a large output. So where does this occur in QLearning methods? Well, let's rewrite the target value as R plus the expected value under pi nu of QS prime A prime. So if you're doing QLearning, pi nu is just this argmax policy. It's the distribution that gives a probability of 1 to the argmax. If you're doing actor critic, pi nu is your actor, right? But I didn't really change anything because you can just choose pi nu to be the argmax and you recover the original equation. And this right-hand side is the target value. So what's the objective for training your Q function? Well, if you're doing offline RL, then your data set was collected by some behavior policy pi beta, and you're minimizing the difference between Q and the target values under pi beta. And what that means is that you would expect to have good accuracy when pi beta is equal to pi nu, right? You're evaluating Q in expectation under pi nu, you're training it in expectation under pi beta, so good accuracy is to be had when pi nu is equal to pi beta. But how often does that happen, right? The whole point is that we're improving pi nu to make it better than pi beta, right? In response to the previous question, we don't just want to copy the data, we want to do better than the data. But that, of course, means that pi beta and pi nu will not be equal. And even worse, pi nu is selected to maximize the Q values. So just as I alluded to on the previous slide, this maximization process is essentially training pi nu to produce these adversarial examples that fool your Q function into outputting a large value. And viewed in this light, it's then not too surprising that we see this massive overestimation, that we see that the Q function thinks it's going to get enormous reward, but in practice, it actually gets a very low reward. So in some sense, the mystery is perhaps solved, but now we have to figure out how to actually build effective methods, how to solve this problem. So let's talk about that. How do prior methods address this? So one very popular class of approaches to try to mitigate this problem is what I'll refer to as a policy constraint method. It's easiest to think about as an actor-critic algorithm, although it doesn't have to be. But in an actor-critic framework, we would train a Q function for our current actor pi nu, and then we would update our actor with an additional constraint that minimizes some measure of divergence or limits some measure of divergence between the learned policy pi and pi beta. Here I have it written as a KL divergence, although other divergence measures could also be used. And in principle, this should solve distributional shift, right? Because that second term directly controls for distributional shift, which means that we get no more erroneous values, right? Well, maybe. So this is the basis of these policy constraint methods. It's a very old idea. As far as I know, it doesn't have a single name, but here are a few places where it comes from. And here are a few recent papers that have used it in various ways. And by the way, I'm not sure what is the first paper to have used it for kind of offline settings. Fox et al. Used it back in 2015. There's probably earlier ones. So it's kind of one of these venerable ideas whose origin may be lost to the depth of time, or maybe somebody more knowledgeable than me knows where it comes from, but it certainly gained more popularity recently. But it has a few issues. One is sometimes actually imposing this constraint is difficult because we usually don't know what the behavior policy is. We might be using human provided data from a hand designed controller, or data from many past RL runs, or all of the above together, which might make it difficult to get a functional form for pi beta. But that's in some ways kind of a technical problem. We can mitigate it in various ways. A bigger issue is that this might be both too pessimistic and not pessimistic enough. What I mean by that is, if you remember before, I said that even if your test point comes from the training distribution, you're still not guaranteed to have high accuracy because the error will only be below an expectation. So in that sense, this might not be pessimistic enough. It might also be too pessimistic because if your behavior policy is totally random, let's say it's uniformly random, well, you don't really want to limit your learned policy to be more uniform. You don't want to limit it to be more random than it needs to be. You kind of want to find the best behavior inside the data set, whereas most divergence constraints will force you to be more random if your data is more random. So it's kind of sometimes not really quite doing what we want. So I'll talk about how to fix issue 1 first, and then I'll talk about some methods that avoid direct constraints like this entirely, and in that way also address issue 2. So in my work, I found basically 2 principles to work well for offline RL methods, and they're kind of different. One principle is to avoid ever evaluating actions that were not seen in the data set. So don't just limit the distribution, but actually figure out how to build an entire RL method that never has to query actions that are not in the data set. If you can do this, then you will avoid any issues without a distribution actions because you never even look at them. So if these black points are your training set, this is your fit. Your fit might extrapolate in some crazy way on the left. It might have erroneous maxes even in distribution because it can be exploited. But if you only stick to the black points, if you only stick to training points, then your values are actually quite accurate. So you're essentially only using your function approximator as a way to approximate integrals. Option 2, train Q functions in some modified way so that OOD actions never have high Q values. So this kind of has the flavor of an adversarial defense. Find these erroneous peaks and explicitly repair them in some way. Now you can't repair them to always get the right value, but perhaps you can repair them so you don't overestimate. And these are 2 different principles. They lead to different classes of algorithms, and I'll talk a little bit about both of them. So let's start with option 2. I'll talk about a method called advantage-weighted actor-critic, which is based on an earlier class of techniques called advantage-weighted regression developed by Jason Peng and Abral Kumar, and advantage-weighted actor-critic was developed principally by Ashwin Nair. The idea is the following. We're going to have our basic actor-critic recipe, and the actor training, in order to maximize this Q value, we'll need to query actions, query the Q function with actions that are not in the data set. So it'll actually evaluate QSA for whatever action is taken by the current policy, which might not be an action that is present in the data set. And that's where a lot of our problems come from, because that allows the actor to learn how to exploit the Q function, right? So can we modify the actor training so that we don't end up querying out of distribution actions or even out of sample actions? Well, here's an idea. What if we train the actor with weighted regression? So instead of sampling actions A from pi and then evaluating their Q values, what if we take the samples from the data set and instead maximize their log probability with some weight. So if we just maximize the log probability of the data set actions, that's of course behavioral cloning, that's imitation. That's not making our policy any better than pi beta. That's just imitating pi beta. But what if we put in a weight and we choose that weight so that the weight is larger for large values of QSA? In fact, we can actually show that if the weight is chosen to be proportional to the exponential of 1 over lambda times q, this actually solves the constrained actor optimization. The intuition is that lambda here serves as the Lagrange multiplier for the constraint, so lambda depends on epsilon. And you can kind of see why this is the case, because as lambda goes to 0, then the weight will be infinity on the action with the largest q value, if you imagine doing normalized weights. And then the best action will get all the weight, and you'll copy the best actions. As lambda goes to infinity, then the weights all become 1, and that's the same as setting epsilon to 0. So essentially, lambda interpolates how far you're allowed to deviate from pi beta, and making these weights dependent on q actually does improve your policy. It actually gets it closer to the optimal policy and further from pi beta. So that's pretty neat. We've developed an algorithm that can do constraint actor optimization without ever having to query actions that are not in the data set. Now, I should say we didn't come up with this property. The fact that this constraint optimization has this solution, it has been derived using Lagrangian duality. Again, it's one of these like very old ideas present in many of the constraint papers that I mentioned before. But adapting this into an offline RL method actually leads to a method that works decently well in that it saves you from needing to know what pi beta is, and it enforces this constraint. By itself, this is not really a great method for fully offline training, but it turns out to be quite a good method for offline training with online fine-tuning. So here are some animations of this approach in action. We have some data of a robotic hand. Behavior cloning that data gets success rate. Behavior cloning that data actually gets a success rate that's very low. Running offline RL with a wake on it gets a success rate of 24%, and running additional online training gets that success rate up to 80% plus. So these are some learning curves. The red curve is advantage weighted actor critic or awake. And you can see it starts off kind of at the same level as other offline RL methods, but then climbs up quite a lot higher. Now, this method is not that great by itself as a fully offline method, mostly because while it avoids out-of-distribution actions in the actor update, it doesn't really do much to avoid them in the critic update. And when the actor is partially trained, it might actually take a lot of out-of-distribution actions in the critic update and result in some trouble. So can we modify the critic update also so that the critic update never has to query either out-of-distribution or out-of-sample actions? Here's how we can do this. Let's look at just the critic update. And let's say that this next value, the expectation under pi nu of q, is going to be represented by v of s prime. And v of s prime is just going to be another neural network. So we could try to train v of s without using out-of-sample actions or out-of-distribution actions. For example, we could train it to minimize the difference according to some loss function L between v of s and q of sa for every SA tuple seen in the data set. Right? That's a valid way to train V. And you could use, for example, mean squared error loss. But that's not actually going to give us what we want, because the action that we have in our data set comes from pi beta, not from pi nu. So it's basically the wrong expected value. We're getting V to match the expected value under pi beta, which of course we can do very well because that's where our data came from, but we needed to match the expected value under pi nu. So this is a way that you can avoid out-of-distribution actions, but it's not a way that you can actually train a Q function for an improved policy. But here's an idea that can let us change this. In your data set, let's say you have a large or continuous state space. Every action every state is probably not visited more than once. But for any given state, there may be other trajectories that have visited similar states. Not identical states, but similar states. And insofar as your neural network generalizes, it might realize that these similar states should have similar values. But you took different actions in those states. So you have other similar states where very different actions were taken. So in effect, you can think of the targets for this value function regression as being a distribution over Q values, each with different probabilities. So the Q values for the states that are the most similar have the highest probability, and the Q values for states that are a little different have different probabilities. But all these states have very different actions, so they will have different Q values. And in a sense, what this value function is doing is it's approximating an expectation. It's approximating an integral. It's approximating the expected value for this histogram that I drew here. So this distribution is induced by the difference in actions that was taken at other similar states. And the mean squared error gives you the mean of this distribution, the expected value of this distribution. Now notice that the randomness here is due only to the actions, because we're not regressing onto Monte Carlo returns, we're regressing to the Q values. So if there's some luckiness due to subsequent transitions, that's not appearing in this distribution. The distribution is just due to the fact that other similar states had different actions. So here's a thought. If we have this distribution over values, instead of picking its expected value, can we pick something like an upper quantile? Can we modify our loss function so that when the value function looks at these different states that are all similar to each other and that all had different actions taken in them, instead of picking the expected value, pick something that's tilted towards the right-hand side of this histogram? If we do that, then we will learn a value function for a better policy than pi beta. And it turns out that that can actually be done. And we can do it just by changing the loss. We still use the same SA tuples in the data set, but we'll use what is called an expectile loss. An expectile loss is like a mean squared error loss, only it's tilted to one side. Looking at the form of this equation, you can see that you have x squared for the negative branch and x squared for the positive branch, but one is multiplied by 1 minus tau, the other is multiplied by tau. So if tau is equal to something like 0.9, you have this asymmetric loss that punishes negative errors a lot more than positive errors. So if you use this loss function in place of the MSE loss for training the value function, intuitively what it does is it will punish the value function more for those states where the value is lower than Q, and it will punish it less for those where the value is larger than Q. It still wants to, all else being equal, match the Qs, but it'll tilt the value towards the right-hand side of this histogram. It doesn't give you a quantile, it gives you something called an expectile, which you can intuitively think of as just the, quantile is to expectile what L2 is to L1. Or sorry, the other way around, quantile is to expectile what L1 is to L2. So the net effect of this is that we can actually show that if you train repeatedly with Bootstrap using this kind of expectile loss, then your value function will approach the max over your Q function over the set of actions in the set that we call omega s, where omega s is the set of all actions whose probability under the behavior policy is larger than some epsilon. Basically the set of all in support actions. And that's very nice. That's actually what we want. We're actually improving our implicit policy in this case, using in support actions without ever having to query out of sample actions during training. So both losses, both the Bellman backup loss and this quantile expectile regression loss, all use SA tuples that are actually in the data set. And that's quite nice because that means that the Q function cannot be exploited because only the points that it's trained on are the points that it's queried on. The only thing you do have to do is you have to make sure you don't overfit when you do this. So then we'll use this expectile loss with a large value of tau. So we call this QLearning with implicit policy improvement. This is a method designed by Ilya Kosterikov. It gets you this in support action. And the procedure is you do Bellman backups with your learned value function. And in effect, that's the same as doing Bellman backups with this max over the support using an implicit policy, except that you don't have to actually calculate the support directly. You just use the expectile loss. So now you can do value updates without ever risking out of distribution actions because you never risk out of sample actions. I'll present results for this method a little bit later. But before I do that, I want to talk about option 2, and then I'll show results comparatively for all of these methods. So option 2 was, instead of avoiding out of distribution actions, let's actually somehow repair our Q function so that they are not a problem. So remember that our problem was this overestimation. So what if we actually hunt down those overestimated values and fix them? So here's an idea. Let's adapt a modified loss function where we have our usual objective, which minimizes the difference between the left-hand side and right-hand side of the Bellman equation, and an additional correction term, which minimizes Q values for actions chosen from some adversarial distribution mu. So intuitively, mu is trying to hunt down these actions that have very large Q values, and this loss function pushes down those values. Okay, very straightforward idea. Mu is literally just adversarially optimized to find large Q values, and then the Q function corrects them. A lot like adversarial training in many ways. It turns out that we can actually show that if we choose alpha to be large enough, then the resulting Q function, Q hat pi, is a lower bound on the true Q function. Nice, under some assumptions, of course. But it turns out that if we do this in practice, this tends to swing the pendulum too much in the other direction. It tends to underestimate too much. So the full method, and this was designed by Aviral Kumar, called conservative QLearning, actually uses a better bound. The full method has a term that pushes down the Q values from these adversarially chosen actions from mu and pushes them up for the actions in the data set. This might seem very strange because we're trying to correct overestimation, and we're doing so by pushing up on actions in the data set. But here's why it makes sense. If all the high Q values are in distribution, then the actions you choose using mu will look similar to the actions you choose in the data set. And therefore, these two terms will more or less cancel out. But if the high Q values are for out of distribution actions, then the first term will push them down, and the second term will push up on things that are in distribution, which will move the good values closer to the data distribution. So it's a kind of a feedback process. If high values are out of distribution, they move in distribution. And once they're in distribution, then these terms start to cancel out and their effect is minimized. Now, we're no longer guaranteed to actually have a lower bound for all states and all actions at this point, but it turns out that we are still guaranteed to have a lower bound on the expected value of Q under the policy for all states, which is all we really want, because this is saying that our estimate of the policy's value will be a lower bound on its true value. So that's quite nice. And then we can use this, for example, in an actor-critic algorithm by using this for the critic evaluation, or we can also use it in a QLearning framework by using the argmax policy, because the argmax now will be robust to these out of distribution actions. Okay, so that's conservative QLearning. Now let me talk a little bit about how we can evaluate offline RL methods, and I'll show you some results. So how should we evaluate offline RL methods? Well, to answer that, the first question we should contend with is, what do we actually expect offline RL methods to do? So the first bit of intuition, which doesn't really capture what they do, is that it's like imitation learning. So you have a start point and end point, and imagine that your data looks kind of like this. Imitation learning would. It can actually be shown that offline RL is provably better than imitation learning, even with optimal data, under some structural assumptions. But this is not really the setting in which I think these offline RL methods really shine. A better intuition is that it's about getting order from chaos. If you have highly varied data, much of it might be highly suboptimal, you could imagine an offline RL method as putting together the best pieces of the data to get behavior that is effective at some desired task. One instance of this is what we could call macro level stitching. Like if you have some data that goes from A to B and some more data that goes from B to C, you should imagine that offline RL can figure out how to go from A to C. And we do see this happening. But that's just kind of the most obvious example. In reality, the effect can be much more subtle. You can imagine a kind of a micro level stitching. Maybe you've seen many human drivers in an autonomous driving setting that are all suboptimal in different ways. And maybe they're good in some places, but bad in others, but they're all good in different places and bad in different places. Can you put together the best of all of them? Can you essentially get a superhuman driver that in every single situation behaves the way the best driver in that situation would have behaved, which might be better overall than any single driver? So we can think of it as kind of micro level stitching, picking the very best parts in every single instance to actually do a lot better than the best trajectory in the data set. So if we have algorithms that can properly perform dynamic programming, we can take this idea much further and get near optimal policies, even from highly suboptimal data. So one perhaps vivid example of this is in this paper by Avi Singh called COG. So here you have a robot that is learning to pick up an object from an open drawer. If at test time the environment changes and the drawer is closed, the robot, of course, won't succeed anymore because it hasn't seen closed drawers while learning to pick up this object. But if it has access to prior data, where the robot did many other things like closing drawers, opening drawers, moving other objects, but never did this whole thing together, it never actually opened the drawer and picked up the object, then just by combining this data set into a single offline RL training set, we could actually get a policy that does the original task, but also figures out that it should open the drawer and pick up the ball if the drawer is closed, because it saw drawer opening, separately it saw ball picking, and it can connect the two via the value function. It can close the top drawer, open the bottom one, and then pick up the ball. You'll see that in a second, there it goes. And it can move some object out of the way, then open the drawer, then pick up the ball. So I'll play short. So get this thing out of the way, open the drawer, and then pick up the ball. So it's basically composing these behaviors in the data set in the way that is most appropriate for the task. We designed a benchmark suite called D4RL to study various aspects of offline reinforcement learning. And D4RL has standard kind of Mujoko Gym style locomotion tasks. It also has these maze tasks that are specifically intended to test compositionality. So in the maze tasks, especially in the larger ones, there might be no path at all from the start to the goal, but there are paths between other points in the maze. So the full task requires going from the lower left corner to the upper right corner, and the individual tasks go between other pairs of points. So you have to recombine parts of those tasks. Then there are tasks that require using human data, such as the dexterous manipulation tasks. So these were actually used in originally proposed and worked by Arvind Rajaswaran, who's giving a talk here actually, as well as some manipulation tasks in these kitchen environments, driving tasks, and traffic control tasks. So broadly speaking, these are separated into simple diagnostic tasks like these gym tasks, tasks that evaluate compositionality, as well as applications tasks. And it's instructive when comparing different offline RL methods to look at their performance across this set to understand whether they're really doing compositionality properly. So now that I've described these tasks and the evaluation standards, let's look at some results. So these are results that compare some methods that are, basically behavior cloning methods. So behavior cloning all the data, behavior cloning just the best data, as well as a recent method called decision transformers, which is, you can think about essentially also as a variant of behavior cloning. Recent offline RL methods, these are offline RL methods proposed in 2021, advantage weighted actor critic, and then on the far right, IQL, which is the expectile regression method I discussed, and CQL, which is this robust method that I discussed. Something to note about the results. On the locomotion tasks, what you can see is most methods that work well kind of get similar results to good BC implementations. So CQL and IQL do the best among all of these, but the difference between those and methods that kind of copy the best trajectories in the data set is not very large. In contrast, if we look at the ant maze tasks, which require actually doing dynamic programming properly and utilizing compositionality, we can see a really big gap. So there's basically the methods cluster into two sets: those that get around 160 or less, and those that get over 300. And there is about a factor of 2 difference between CQL and IQL, as well as and all the approaches that are not successfully doing dynamic programming here. So there are differences, and which offline RL method you use actually matters. If you're in a setting where you want that compositionality, then you need a method that does dynamic programming effectively. So be careful when evaluating offline RL methods, because they can do things that imitating the data simply cannot do, but you have to have the right benchmark that measures that. We can also look at fine-tuning performance. Here I'm just showing advantage weighted actor critic, CQL, and IQL. Advantage weighted actor critic actually fine-tunes decently well, but its poor initial performance from just the offline phase hampers its final results. So here you can see on the left of the arrow is the performance after offline training. On the right of the arrow is the performance after additional fine-tuning. CQL gets great performance from offline training, but it tends to be a little too conservative to fine-tune well. So it doesn't really improve all that much from the fine-tuning phase. IQL actually generally ends up performing the best when fine-tuning, because it has a fairly good performance after offline training and still fine-tunes effectively. So we have these two options that I discussed: avoiding ever evaluating actions that are not in the data set, and training the Q function so that OOD actions have never have high values. And at this point, you might be wondering, what are the trade-offs between these two options? So IQL is there's a little bit of reverse chronology here. IQL is actually option 1, CQL is actually option 2. But here are the trade-offs as we understand them now. CQL has fewer hyperparameters, and it tends to have cleaner workflows with offline tuning. So we actually have pretty good standards for how to tune the hyperparameters of CQL with only offline data. It also has better theoretical guarantees. IQL performance seems to be slightly better, and it also fine-tunes much better. So that hopefully gives you a little bit of guidance, but probably more research is needed to really understand which option is the better one, or if these options should be combined in some way. So we still don't know which pipelines are going to be more effective in the long run. Okay, in the last portion of this talk, which will be pretty brief, I want to just briefly talk a little bit about applications and say a few words about, basically why I'm excited about offline RL methods and why they can have such a big effect on applications. So if you want to use RL in the real world, your process probably looks something like this. You first instrument your tasks. Maybe you add some safety mechanisms, some autonomous collection, and so on. And then you wait for a long time for RL to run. And then you change your algorithm in some small way and then repeat this whole process. And after you're done, you have to throw it all in the garbage and start over for the next task. So that can be really tedious and extremely time consuming. With offline RL, you collect a data set using whatever source of data you have, train a policy. Then when you change the algorithm in some small way, you just retrain the policy. You don't collect more data. If you do want more data, you can simply add it to the data set. So you don't recollect it, you simply append data, which is a lot quicker, and then train the policy. And if you want to do another project after that, you can just reuse the same data. So this process becomes a lot less tedious. You spend a lot more time basically waiting for compute to run rather than actually interacting with the physical system. And that's a lot easier. So let me show you this process in action in a few settings. So I mentioned this QT-opt system for robotic grasping. More recently, we extended this to learn many different tasks in a robotic manipulation setting. This is a system called MT-opt. It was able to do 12 different tasks with thousands of objects and months of data collection. But that's not actually what I want to talk about. What I want to talk about is what happens afterwards. Afterwards, we had this new hypothesis. We were wondering, well, could we learn all these tasks without using reward functions at all by using goal-conditioned RL? This talk is not about goal-conditioned RL. That's kind of not the point. We just had this new hypothesis. And what we did is we didn't actually collect any new data. We just took the data we already had and we trained a goal-conditioned policy with it. And that immediately allowed us to evaluate our new hypothesis without any additional data collection. We could see that, well, we could actually get goal-conditioned policies to work well in these real-world robotic settings. And all of that was done using an offline RL method, similar to CQL, actually. And then we found out that this actually serves as a pretty good unsupervised kind of pre-training objective. You kind of think of it as like BERT for RL, basically, where you could pre-train with CQL with goal-conditioned learning and then fine-tune with a reward function and get better performance. So the cool thing here is that we had this hypothesis about real-world data that goal-conditioned RL can serve as this pre-training, and we were able to resolve that hypothesis without any additional data collection using just offline RL. Another example, in early 2020, my student Gregory Kahn collected 40 hours of data of an off-road robot driving around in this kind of a rural facility that we had outside of Berkeley. And then in late 2020, Dhruv Shah wanted to build a system for goal-conditioned navigation. And again, he just took the data that Greg had collected, that 40 hours of data, and without any additional data collection, was able to build a system that could do things like delivery tasks and inspection tasks. And then in early 2021, Dhruv could again take that same data and train a kind of almost like a meta-learning style policy that could learn to explore in a new environment to search for various objects, again, using all this previously collected data. Now, there are other topics in offline RL that I don't have time to get into, but there's a lot of interesting work in model-based offline RL, which I didn't get a chance to discuss, but there's a lot of cool stuff there. We can train conservative algorithms in a model-based setting. We can train large transformer models in a model-based setting. There's a lot of interesting work to be done in multitask offline RL, where you can think about how to share data in a way so as to avoid distributional shift. And there are many more open topics. But in terms of the gap between the dream for offline RL and the current methods, for those of you that are thinking about research topics in this area, I think one really good one is offline RL workflows. So in supervised learning, we have this training validation split, which gives us a really powerful workflow to develop supervised learning systems, right? We can train and then we can validate on a held out data set and tune our hyperparameters without having to actually deploy our system. What's the equivalent of that in offline RL? We have a starting point in this Coral paper, but a lot more work is needed, and our current methods for this are somewhat heuristic. Can we develop better statistical guarantees? Can we also develop scalable methods and large-scale applications? I alluded to a few examples here that are all robotics-centric, but I think there's a lot of room for exciting applications also in non-robotics domains. All right, I'd like to thank all the students that carried out this work. I'd like to thank all of you for listening and for staying late. And if we have a little bit of time, I'd be happy to take some quick questions.
Yep. Yeah. Any questions? So you can unmute and you can just ask. Okay, I have one question regarding you talked about this distributional shift, right? Is it something related to, like, say, suppose like what we talk about this domain adaptation, like, you collect the data and use some data